Okay, so I think the right way to think about it is in terms of these necklaces, basically. So in other words, so I don't know exactly what the best data structure, but what it is it's going to be something like I mean, it could be something like the way that we represent BA, those are alternatives, and then B, and so on. Am I making sense? I don't know if that's the best way to do it, but that's a possibility. Do you see what I'm saying? So, I mean, let's take an example.
Well, it is a possibility.
Should we take an example?
I'm not sure how it's related to the Wolfram model case.
I'm not sure either. So, but let's look at these different cases, because I mean, it's important that we have one case that's at least somewhat simple to understand. I mean, this is
Are
not
you sure it's simpler than Wolfram model? It doesn't seem to me.
I want to look at strings, because I think within the case of strings, we have okay, hold on, let me just look at
the same as Wolfram model is that the space is in a sense an emergent concept, because all we really have is just events that match some edges, and the space is reconstructed afterwards.
Yes.
But with strings, we cannot avoid space.
Well, okay. I mean, look. Okay, so let's look at the thing like this. Okay. Okay, so
hello?
what?
Yeah.
Oh, hi, Bernat joined us. Okay.
Yeah.
Actually, I'm now stacking multiple things here. Well,
Yeah, I can wait. There is no problem.
Okay, here, just hang out for a couple of minutes, and then what I want to talk to, for Max's benefit, what I want to talk to Bernat about is the continuum limit of multi-way systems. And I don't know if you've seen these things, Bernat. This is a typical multi-way system with strings. See it? And the thing I realized is I think your trees might be a way to think about a continuum limit of these things.
Right. Like like the limit set of that.
Well, or in particular, instead of having discrete values here, you're looking at, there are continuous values there, and yet you get this kind of convergence.
Right.
Anyway, for Max, we were just talking about this. So if I look at this, right? So this is the first stage at which I get a multi-space thing, right? And the multi-space thing here would be, so I mean
list A, B, B, A. Because it's a whole thing as a branch.
Wait a minute, but the B is shared, isn't it? Isn't it A?
No, it's not. It's, hold on. Yes, it is shared. Wait, it's.
Let's look at it.
It's different B's that stay. Yeah, you see, that's what's complicated here, because yeah, I don't know how to think about it.
Well, okay, so
because it's different B's that stay.
Yeah, I understand. So it's not clear to me that it's right to converge them like that. But I mean, okay, so let's treat the Wolfram model case. Is there a similarly linear one of those that we could look at just as an example? I mean, we could certainly look at it emulating the strings. But what do you think the data structure is going to be? I mean, so in other words, go ahead. What are you going to say?
Well, I mean, I don't know any examples off the top of my head, but it's probably not hard to make one. But data structure, as I explained before, it's just events. Events with information about which edges they produced and destroyed.
Yeah, but that's all well and good. But I want something which is an actual, you know, which.
How to specify an initial state?
Yeah, for example, I want to be able to specify. I want to be able to just write these things down in such a way that I can see.
Yeah, I see what you're saying. I actually have an issue about it already on GitHub, but basically, okay. So as we were talking last time, the kind of the simple way to do it is just have a for each pair of edges to specify how they're related to each other. That will tell us everything we need to know, but it might be inefficient.
Yeah, but I mean, the whole point is here, if we look at if we look at this,
Yeah, so here all edges are pairwise space-like.
What do you mean by that statement?
In each state.
So your claim is in each state, these edges are space-like separated.
Yeah.
Yeah, I agree with that statement.
And between different states, they might be either time-like or space-like separated here.
Okay, but here within each generation, it doesn't need to be a generation though. Within each state, the edges are space-like separated. But now the question is, what happens when they're branch-like separated? What happens when we want to specify something which is branch-like separated? So what's going to happen is, what is the branch-like version of this? So in other words, if we take this thing and we say, okay, so now this gives us a bunch of states. Here, we've got that singleton state, and then we've got this pair of states, right?
Well, this is a perfectly reasonable distinction, although we need to identify which of those stages are the same.
I don't understand what you're saying. So
I mean, if you have two versions of a state on the same step, we need to identify which of those edges are the same and which just have the same vertices, but they're actually different edges.
Okay.
So if we just use indices of those edges in all expressions instead of actual edges, that would give us all information we need.
Well, but we need to be able to draw. Okay, but hold on. What are we going to draw here? So each one of these is a graph, or in general, a hypergraph. So there's a list of hypergraphs here. But some of those hypergraphs have shared edges, right? Some do not. Am I making sense?
Yes.
Okay, so what we need to draw is...
most of them have shared edges with something if they're large enough.
I'm sorry?
I mean, most of them will have shared edges with something.
Yeah, I understand. But so what we'll see here is a picture that looks like this, right? But instead of being a single edge here, we'll see, I mean, when they are shared edges, will we identify the elements at the ends of the edges or not?
Well, of course.
Okay, so
It's
what
the
you would
same
expect to
elements.
see is a multigraph here of some kind. Is that true?
Well, yeah,
I don't
one way
understand
to
that
show them would be we can assign, and I know you don't like colors, but that's one way. So we can assign a color for each of those states, and then if edges are distinct between states, we draw them different color. If they are the same,
it draws a multi-edge where it has multiple colors of that edge, right?
Right. Well, we would draw multiple edges.
But I don't know if this is correct. I
Very
don't know if you
different
can
edges.
factor. Does it factor in that way? That is it the case that?
Well, if there was an event somewhere which branched locally, then all the other edges are the same.
I think I need to see this. So I don't disagree with your idea for now. So let's just understand. On a given step, there could be different colors corresponding to all of the different states that exist at that step, right? Like in the multi-way graph, there could be a color for every. So another way to think about it would be, maybe, I don't know, we could think about it, drawing it, embedding it, not in the plane, but in a stack in a 3D stack. Am I making sense? Where every state, in some sense, gets. Is that crazy? Every state gets.
Well,
its
that's
own
a good idea. The problem is that it's the edges that needs to be on stacks, not vertices.
Oh, I know that. So you'd have to, but that means that we're having. I'm sorry. So wait a minute. So that's one possibility. Different possible edges of different possible states.
If we can exchange vertices and edges, then we can definitely do that.
Oh, wait a second. Edges of different possible states exist at different z coordinates. Okay, what would it mean if we exchanged
well, we
edges?
draw each edge as a vertex.
Well, I understand what that means. I mean, I understand how we can make a dual graph, but I don't understand what the significance of the dual graph would be.
Well, then we can put edges will become vertices, so we can put them on different layers.
I understand that, but what I'm not understanding is what the interpretation is in terms of space. Then,
Well,
I mean, it's a sort of projective.
It's a different way of looking at it.
But it's a kind of projective version of space in some sense.
What do you mean?
Look, we're exchanging space-like edges here, right? For points.
Well, how do you know that its edges are space-like and not the points?
Well, I mean, look, we could write the rule in terms of edges too, except that we choose to keep track of it in terms of the points.
Well, no, the way I see it, they're just different ways of looking at it. We can think of a rule operating on vertices where each vertex is specified as a list. And edges are just tells us which vertices are related to one another through shared elements in the list.
So fine, but so let's then make, so if we take a typical, how can we make the dual graph? Is there a function for making a dual graph?
Well, I'm not sure.
Well, but you understand my question.
Probably for normal graphs there is.
Well, this is a normal graph, so we can use it. How would we do it? Just constructing it. What is line graph? What is a line graph? Each vertex corresponds in line graph, corresponds to an edge in G. Sounds promising. So then we would say here, can we do states graphs list? Can we do a graph? No, we can't here.
No, we can't.
Okay, so now we say line graph. What the heck? What is this doing?
What is the first one doing?
What? I
There
don't
should be
know.
two vertices on it.
There
Oh,
are
I
two.
see. But
Okay.
they should be connected.
You know what? I think we have to make these undirected graphs. I think that's the problem. Okay. Okay, so that's the dual graph of each of those. So we can continue a little bit longer just for fun. What on earth is the interpretation of these? Do you understand what I'm asking?
Yeah. I mean, I think it's just a different way of looking at space. I don't see
Is
why
it?
would they look fundamentally
Is
different.
it, or is it a projective way of looking at space? This is saying, no, it's not the same thing, because these elementary edges, right, have a length that's c times the elementary time. But now here we've done something different. We've got something where what are the lengths of these elementary edges? Do you understand what I'm asking?
Wait, actually, what happens when the vertices have degree larger than 2? Shouldn't they be hypergraphs?
Well, I don't know what this is exactly doing. This is taking, maybe so.
So what they should be is undirected hypergraphs, but each vertex should be indexed.
Well, okay, so.
And if you do that, that seems to be the equivalent way of looking at things.
Wait. I don't think it's equivalent. We construct
Well,
an
how do
undirected.
you know is that edges that have certain lengths in space and not the vertices?
How does a vertex have a length?
Well, why wouldn't it? You go from one edge to another, you pass through certain number of vertices. So that's a length.
It's a little weird.
Is it?
I don't know. I mean, I don't know. Okay, but so let's say we do that. Okay, so we have a dual graph to space, right? Where the connections are hyperedges. Okay, so hold on. Dual graph to space, connections are hyperedges. No, the connections are nodes. The vertices, the previous nodes, previous connections are now nodes, which participate in several hyperedges. Previous nodes are now hyperedges. So it's just saying that each node, okay, that's all right. Okay, fair enough. So what does this buy us?
Well, now we can put each edge, or I mean, each previous edge on a different layer because it's a vertex. And since it's edges that are on different branches, we can now properly layer it.
Okay, so what you're saying is that, okay, so now we can make physical space be XY coordinates and branchial space be Z coordinates. Is that right?
Right. Although we need to keep in mind that the same edge can be at multiple branches at once. So there would have to be lines, well, quite lines actually. Yeah, okay, it's not that simple.
Yeah, but I mean, okay, so a given, I mean, I think the first thing we have to do is build the data structure. It doesn't matter which way round it is, right? Could be either way around. I'm not sure this is so important. This dual thing is so important.
Well, what's important is that edges are on different branches and not vertices, because I don't see how can we do it any other way.
Well, whatever. I mean, look, the main issue is, okay, so can we draw the data structure that is this thing? Okay, so the issue is to compress this, right? To get a compression of this in some data structure that we understand. Am I making sense? Even if that compression, even if for now that compression is done in a very hacky way, et cetera, et cetera, et cetera. But could you write something that will make a annotated compressed version of this? Do you see what I'm saying?
Well, you mean as a visualization?
No, I mean, first step is to just make the data structure, okay? Then to try to understand what visualization we might do. But the first step is to make the compressed data structure. Am I making sense?
Well, yeah. Which is the same as making an evolution, because that's how you would.
Or whatever. I don't care. But I mean, the fact is that in here, clearly many of these edges are shared, right? You understand? Right. So I don't know whether the right way to represent that sharing is simply to give them symbolic names and repeat them, right? Do you understand what I'm saying?
Well, yeah, that's one way.
Right. So if we did that, then what I think we have is a hypergraph of hypergraphs in some sense. Because what we've got then is each one is a hypergraph, right? But yet there are hyperedges in each hypergraph that are themselves joined in other hyperedges. Do you see what I'm saying?
Well, okay, that's one way of looking at it, I guess.
Okay, so let's take that way of looking at it, okay? Because that way of looking at it gives us then that means that in terms of graph layout, right, what we've got is two kinds of edges, which are essentially the space-like and branch-like edges. Do you see what I'm saying? So in terms of graph layout,
what do you mean branch-like edges? No branch-like edges, they're pairs of edges which are branch-like.
I know, but I'm saying that look, if we connect the 1, 3 here to the 1, 3 here, right? Because they're the same, that's kind of the opposite of them being branch-like. That means if those things are shared, right? what we're doing is we're collecting. I mean, I don't know whether those two things should be considered the same object, the same node in the second level
What is the same
hypergraph.
object?
I'm sorry?
I mean, well, in other words, if you know, somewhere in another galaxy something branched, it doesn't mean that all of a sudden all the edges in this galaxy became different edges. Like, that's very weird.
Yeah, okay, fair enough. Whatever you say, but I mean, the basic bottom line here is we need to represent the data structure that comes from this, you know, in this representation of the multi-way system, these things do no longer represent their branchial lineage. You understand what I'm saying?
Right.
Okay, so we need to represent that lineage somehow.
Okay, I think what we need to understand is what is it we want to do with it.
We want to make a data structure that we can visualize. That's the first step.
Yeah, but what do we do with visualization?
We look at it. Okay, what we want is the analog of space with branchial data in it. That's what we're trying to get. We're trying to get something which, when we appropriately project or crush or slice it, we get ordinary space. Am I making sense?
Well, the problem is, if we display all the data we have, it seems unlikely that it will be understandable.
I don't care. I don't care. I don't believe in that. I'm sorry. I just don't believe that. It's the nature of these things. That yes, there are cases where they will be complicated, and there were cases, you know, when it's simple enough, it will be understandable. When it gets more complicated, it won't be understandable. But it doesn't matter. We just need a structure where we can display these things. Okay, so the goal of the structure is that one slice of it should give us ordinary space. But the whole thing, and another slice should give us branchial information about some part of that space. Does that make sense? So in a sense, there are two projections that we can do. One is we're projecting onto essentially space-like separated things, and the other case we're projecting onto branch-like separated things. See what I'm saying?
Yeah.
What I think we want to do is it's some kind of thing where we take this, or maybe the dual graph, but I prefer it not being the dual graph, and we make essentially a stack of copies of this, but it isn't quite copies. It's exactly what I was saying for the strings, right? There are pieces that are shared, and there are pieces that are not shared. Am I making sense?
Well, yeah, does make sense.
Okay. Could you have a think about this and see if you can actually implement something?
Well, definitely.
Okay. Why don't you think about it, you know, sooner rather than later, because this is all right.
I mean,
Okay.
I still think it would be much easier to do if we have evolution first.
What do you mean?
Because
evolution?
like what are we going to do with this visualization if we don't have evolution to like to
I don't
use it
understand
for?
what you're talking about. What are you talking about? I mean, obviously you've got to generate these things by evolving something. What do you mean?
Well, exactly. So what I'm saying is it would be better to implement that evolution first.
Yeah, but you don't need to implement a giant piece of C code. We are just looking at toy cases here. Just implement it in the way, because the first implementation of this will not be correct. It will not be what we want. And there's absolutely no point in building it in high performance C code, you know, in the first implementation.
Why wouldn't it be what we want?
I don't know. Okay, I don't know, because it is my intuition that we will not get this right first time.
Because we already have it working there, so it's
all right, well,
just
fine.
pretty small changes there.
Okay, all right, fine. If you can get it working, get it working. But let's see something in the next, you know, day or two, so that we can start to look at this and iterate on it. You know, not wait for a long time, right? I mean, otherwise, I will try and implement something in simple top-level code, but I would much prefer if you would do it.
Right.
Okay, and you know, we still haven't completely understood what the data structure that it is trying to produce is, have we?
Well, I understand what the data structure is for the evolution.
What does that mean?
I don't completely understand what is for visualization.
Okay, what do you mean? What is the data structure for evolution?
Well, as I said, it's a set of events with, for each event, input and output edges.
Right,
That's
but that is
sufficient information.
right. That is essentially a causal graph, is it not?
Well, yeah.
Right.
It's
So what you've got?
causal, well, with edges.
Well, I'm sorry. It's a causal graph, is it not? You've got events and you've got connections between events.
Well,
Am I correct?
Yes, but it has edges in it as well.
What do you mean? What do you mean it has edges?
So it's a causal states graph.
What does that mean?
Whatever it's called. Well, the one you have at the top is states and events.
Okay. Okay, fine.
Yeah, except that states are not complete states, but just inputs and outputs.
And how do they knit into other things? How does it know how they knit, how those inputs and outputs knit into the rest of the state?
Well, it doesn't. We reconstruct it afterwards.
Okay, that's not good enough, is it? I mean, okay, so
Well,
let's go through what that would look like for strings. If you didn't have the complete states, if you only had the parts of the states that were participating in an event, right? That's essentially what we're drawing here, isn't it? Is that correct?
Well, here you wouldn't have complete information.
No, I'm asking the question. The thing that you are describing, right, of keeping only the inputs and outputs participating in an event, that is exactly what is drawn in these events. Is that correct?
No, this event draws the entire string.
Look at what I'm pointing at. I'm not pointing at that thing there. I'm pointing at the piece that's stacked up.
Well, okay, yes.
Right? That part is what you're talking about, correct?
Yes.
It just doesn't draw. So what you're doing is you're drawing those pieces, but now the question is, how do you knit together the additional part of the state? Where does that come from?
By selecting a subset of edges which are space-like with one another.
Okay, so let's look at it in this particular case, right? Let's look at what this would look like. Okay, so it's this graph without the blue things. There are no blue pieces, correct? Correct, you're not keeping them, is that correct?
Well, yeah.
Okay, let's be clear. I mean, we're not keeping those, right? We're only keeping these pieces here, right? And their connectivity information, correct?
Right.
Okay, so let's understand how we would reconstruct the strings case if we only had that information. Right, so let's look at this picture and see what it would look like. So we would see A goes to BBB, and then we would see just BB goes to A, BB goes to A. So how would we know what was going on?
Well, strings have more information in the states than Wolfram models because they know elements. So we need to know what the positions are.
What you're saying is we have to annotate every position in the string. Is that correct? That if we labeled the positions in the strings, we will be able to do this. Is that correct?
Well, sort of. The problem is that positions change if we add something to the left.
Okay.
So it's more complicated than that.
Okay, but assume that we had a necklace that represented, yeah, I understand. But look, we can have a coordinate on the string, and we can just have negative coordinates if we add to the left. Is that right, or is that not correct?
What do you mean negative coordinates?
Coordinates that are negative numbers. Like if we add something to the left of the A, it's at position -1.
So how does it help us?
You told me that the problem was that you might have to rearrange the coordinates because you add things at the beginning of the string. I'm saying that's not the case. Now, if you have to add things in the middle of the string and that changes the coordinate positions, I understand there's an issue. Do you in fact have to do that? Okay, so if you have to do that, what you need to do then is to label each element here, right, as we did in the emulation of this by our Wolfram model version, right? You label each symbol here by a number. I mean, I admit it gets a little bit messy, and you might as well just use the whole Wolfram model apparatus at that point. But I'm trying to understand. Okay, so just take this example of something, of a Wolfram model that is going to make something which emulates strings, right? So that the structure of space is simple. Am I making sense? So we're not mired in having to, you know, lay out 7 different kinds of things. See what I'm saying?
Right. Yeah.
Right. So take that example and see what it would do in your, you know, take a case where that's the rule, where it's a rule that has that structure, and then see what it does. See, I'm just not sure how you reconstruct. It's all well and good to say, yes, you have the states. My question is, what we're trying to do is to reconstruct something which is a first cut at, you know, space.
You know, I need to point out that right now we don't have states in C++ code already. It's reconstructed now.
Okay.
You know, all the states list is reconstructed.
Okay, great. Then it should be easy to do this. Right, so then what you want to return is this double hypergraph, presumably, that is a reconstruction of the states and a reconstruction of the stack of events. Is that right?
Well, in a sense, yeah.
Could you see if you can actually implement something, please? Okay.
Well, yeah.
Okay, great. All right. All right, I want to talk to Bernat. I was hoping to talk to you, Max, about something different, but as well, but it's okay. That can wait for a bit. I was going to talk to Bernat about his trees. You can stick around if you want to, or not. If you will be able to go off and implement this, that would be very, very nice.
Well, I can't implement in one day.
How long will it take?
Well, for the whole thing, probably a week or 2.
Okay, that's too long. I want something where we can look at a toy version more easily, because I don't think we're going to get...
We need the toy version to be correct.
We need a toy version that is just a toy version. It doesn't matter if it's tested. It doesn't matter. The issue is going to be...
But if it's not tested, the results will be wrong, and then it's
doesn't matter.
Really
I don't care.
to look at it.
I don't care. So long as the results are roughly right, if there are corner cases that are wrong, it doesn't matter. The most important thing is we're not going to understand what we're trying to get out of it until we've seen some examples. Right now we have 0 examples. Right? Right now all we have is this, which isn't an example, right? So I mean, even just seeing a mock-up, a by hand constructed example would be very useful to just see roughly what it is we're dealing with. Am I making sense? It does not have to be production code. I mean, how many times do I have to say this? We're not going to get it right first time. You're going to end up rewriting the production code because the structure is wrong. And we don't want a situation where you spend a huge amount of effort making a structure that turns out to be the wrong structure, and then there's a big, you know, agony fest as I try to explain to you why you have to rewrite it. It just doesn't make sense. I mean, we need to get something where we can look at a toy version to understand the structure. I mean, do you think you know what structure you're going to generate here?
That structure does not appear, would not appear in C++ code at all.
I don't care. I'm asking you what structure. Look, I'm asking you what structure do you think you are going to generate, which is our attempt to represent this multi-space concept.
Well, in the first iteration, list of events with input and output edges, the same as I generate now for non-multi-way case. Okay,
so can we see that output right now? Can we run some code to see that output?
Not right now, because there is no code right now to distinguish between branch-like and space-like edges.
Well, it doesn't matter. I mean, just to get that result, and we can by hand distinguish them. I just want to see what it looks like. You're saying you have something which has a collection of events together with their input and output data. Is that right?
Yeah, I have an old branch that can produce it.
Okay, can we
With
see an
exception
example
that
of
it matches, because it doesn't know what separation in edges are. It matches all of them, including time-like pairs.
Okay, that's
and
not going
so
to
on.
work very well. That's not going to work very well. But so what does it actually generate? What structure does it generate? Does it generate UUIDs for events? What does it generate? How does it represent the events?
Okay, take an evolution object and look at part one of it.
Okay. Okay.
Yeah, so essentially it does the same thing, except it would have multiple destroyer events.
I don't understand that.
Everything else exactly the same.
Okay, the list
Right
of
now, each edge can only have one destroyer events because
okay,
once
so
it's
those
destroyed,
indices,
that's it.
the indices in the creator events are for edges. Is that correct?
Yeah.
Okay. So wait a minute. Atom lists is the list of edges. So there are many more than 8 of those. I don't understand this. There are creator events that are creating edges with serial numbers up to 8. Is that Is that what that means?
That's event numbers.
Okay. Okay.
For each edge.
Okay. Where do I find out? So, okay. This, I see. So this is the list. In that list, that is a list which is keyed to this atom list, correct? Right? So if the nth element of this list is the creator
the other way
event.
around. It's the same index, the same position in creator events and atom list correspond to the same edge. So the last 8, for example, means the last edge.
This one here. This one here.
8. Yeah.
This one here has creator event 8.
Yes.
Right? Okay, I get it. Okay. So that edge. All right, fine. Okay. And what are you saying about, okay, so what are you saying about the multi-way case of this?
So right now, each edge only has one destroyer events. In the multi-way case, it would have multiple destroyer events.
Why does it have multiple creator events?
How would that work? I mean, if edge is created by an event, that if the other event creates an edge, it will be a different edge.
But wait a minute, the number of events you have is not equal to the number of events in the multi-way system, right? It's only the number of events in a particular update sequence. Is that right or is that not right? How many events?
Well, it's a multi-way case, there will be more events.
Okay, I understand. There'd be more. That's what I would think. Right, because you've got.
Yeah, of course.
Okay, so you're saying then there's a longer list of events, but some of those events are essentially branch-like separated. Am I making sense?
Yeah.
Okay, so the events list. So the events list has time-like separated events, and which is what we've got right. Well, the ones here might be space-like separated, they might be time-like separated, correct? We don't know from this list.
Right.
Has time-like plus space-like separated events. We also want branch-like separated events, right?
Right.
Okay, so what would that look like when you have events that you have multiple branches here. You're not going to have serial numbers for every
Oh,
event, are you?
No, we do.
Even on different branches.
Well,
How
of
would that
course.
work for parallel code?
Well, parallel code can be a different thing. And
No, but I
that's
understand.
not a problem for it.
Why?
Because we can generate a random number for events.
I understand, but that means they're not sequential, right? Those numbers are just IDs. They're not necessarily sequential numbers, correct?
Yeah, it's not used anywhere as a sequential.
Okay, fine. All right. Okay, so what's your point now? So what would be the data structure for creator events in the case where you're making a multi-way system?
Creator event are the same.
Why? Why? Why is that the right way to do it?
Because there is only one creator event for each edge.
Yeah, but I understand that. But the fact is that you're trying to distinguish branch-like separated creator events. How would you distinguish?
No, I'm not. I'm just generating all of them. And they distinguish at reconstruction.
Okay, but I don't think it seems like a wrong data structure to me, because that means every branch, if you have a sequence there where you're generating edges sequentially, then you can't do that in parallel. Am I making sense?
It doesn't matter what IDs are.
No, but it matters what the position is here, because the position here agrees with the position here.
Position is reconstructed when it's passed to Wolfram language code. Position doesn't matter also. It only matters that these events correspond to edges.
How does it know what the correspondence is?
Because there's a pointer from one to another.
I'm sorry, what?
There's a pointer from one to another.
Pointer of what kind? How do I see
There is
that
an
pointer?
expression struct, and it has a pointer to events, or just event IDs in it. Doesn't, I mean, it's not actually
okay, so there's a hidden piece of
doesn't
state
indicate.
here, which is the event structure, correct? Listen, I need to get to working with Bernat in a minute here, but
Well, it's not hidden. Everything is here.
Okay, where do I see that
It's the
event
same
structure?
position.
No, but that's a positional thing, right? You just
Well,
said
if you
it
want
wasn't
to
positional.
reconstruct one event, then, I mean, you need to reconstruct it.
Is it positional or is it not positional?
So one position corresponds to one edge in all these lists.
Right, but those positions. I'm saying clearly, when you have a branch-like thing, that's a very unnatural thing to do, to unroll all the creator events for every branch into a single list. Do you see what I'm saying? Seems really weird to do that. Like then you have to decide what the what the scanning order is down the branches. Do you get what I'm saying? You've got many branches
sure. I mean,
in parallel.
we can use data structure that's based on events. I mean, it might even be better, but it
I don't
doesn't really make any
understand.
difference.
Right now, you're going to do what's essentially a depth-first scan of all branch edges. Is that correct?
What do you mean, for reconstruction purposes?
No. To generate this list of creator events.
No, not at all.
Okay. How are you going to do it?
The only thing I'm going to do is so right now, once the match is used, it's deleted, and all the edges that it matched are deleted from the match index as well. So in a local multi-way system, I'm only going to delete that one match that was used and not delete any edges. And in order to generate new matches, I'm just going to check whether the input edges are space-like and only match them in that case.
Okay, so what do you expect to generate as the output in the case where you're capturing the whole multi-way system?
Well, the same thing, except destroyed events are lists for each edge.
What do those lists represent?
List of event indices or IDs.
What do they represent? I understand they're a list of events.
List of events that destroyed that edge.
Why isn't there a list of, so you're imagining that there's a single event. You're treating the event, even in the multi-way case, the event that creates that edge. You're creating two different events that create, well, we don't consider it the same edge, right?
Yeah.
Two different events create two different edges. Now, why are there multiple destroyer events for a given edge?
Because the same edge can be matched in multiple ways.
Can be matched in the multi-way system in multiple ways.
Yes. So there would be two events that destroy it on different branches.
Okay, or more to put a different way, the input for two events, that branch can be used as input. That thing can be used as input for two different events that exist on different branches. Yeah, okay, I get it. Okay. So right now, if we simply look at creator events and destroyer events, what structure, how do we build the causal graph from creator events and destroyer events?
So let's see. So each edge is an edge in the causal graph, and it goes from creator event to destroyer event.
So each edge here, you look up which was its creator event and which was its destroyer event, and that is the connection in the causal graph.
Right.
Okay, so in the multi-way causal graph, are you saying...
There will be multiple of those edges.
Well, you're saying in particular that you go from that same creator node, but that creator node may in general go to multiple destroyer nodes, right?
Right.
Okay. So, yeah, that makes sense. So that from a given event, so essentially the causal graph is knitting together creator and destroyer events. This is a causal graph in which a creator event, yes, so but when we are looking at the multiple destroyer events, there's a difference between seeing a destroyer event at a different place in this list and seeing it in the sublist here, right? The sublist represents branchial, a different branch, right? Potentially. It might be the same branch, but it might be a different branch. So in a sense...
Hold on. If there are a list of destroyer events for a particular edge, that guarantees that those events on different branches.
I understand that, but we don't know. So if we see only one event there, so in general, in general, those things might be singleton lists, or they might be lists of multiple destroyer events, right?
Yeah.
But we can't know which one is the preferred, quotes, same branch event in the abstract. Right? Even if it's a singleton, we don't know it's, quotes, the same branch. I don't even know what that means.
Same branch is what?
As the creator event. I don't think it means anything. Right? So what we're saying
no, it doesn't mean anything. That time like.
Yes, I know, right? I know. So what we're saying is, as soon as we go to a multi-way version of this, we will have that list of destroyer events will all be sublists. Correct?
Yeah.
Okay. So now the question is, right now, the way that you knit so explain to me how you knit the spatial hypergraph out of the events that you have here. Do you understand my question?
Yes. Let's see. I need to remember how that works. Well, roughly it's the same generation correspond to them, but it's not quite the case. Okay, hold on.
Where did that atom list come from? How was that generated? Is that generatable from the creator and destroyer events, or is that an independent thing?
Well, no, because it's only thing that has vertices in it.
Okay, so how was it generated?
Well, that's just the result of the evolution.
Okay, but so in the multi-way case,
edges.
what would you expect this to look like? A much longer list of
Oh,
edges.
exactly the same, yeah. Well, yeah, just list of edges.
It will be longer, correct? Because there are edges that wouldn't exist, that
Well,
only exist.
generally speaking, yes.
Right. Okay, but the way this has to work is right now you're indexing into this list of edges from these numbers in the creator and destroyer events, correct? In other words, the position in the creator list, in the creator event list, is indexed to the position in the edge list, correct?
Yes.
Okay, so that's not going to work. Oh, I see. The
It is going to work.
one, yeah, the creator one, it can still work. It's just the destroyer one.
It is going to work for all of them. Just destroyer events will be lists in each position.
Right, and so that means that edge, that edge goes to. Okay, so if we were to make the analog, so it seems to me a useful picture would be to make the analog of this picture, right? Which illustrates both the edges, each edge, which can be knitted together, right? These edges, I mean, we could in principle, I could take this whole list here, right, of all lists or all edges that exist at any step, right? And I could perfectly well make a graph that is.
Well, you could just the Wolfram model plot, yeah. And we actually did it before. And try to put edges or events in it as well, and it looked incomprehensible.
Okay, well, so we're going to have to do that again, right? So this then, so what we'll have to do is this picture together with, and then what we're doing is in this picture, this is space for all time, basically, right? And then what we're doing is we're saying this is essentially the transitive closure of space in some sense. And then what we're asking
for. Why transitive closure? What do you mean?
Well, because it's every edge in space that was created at any time. It doesn't matter. That's the basic concept is it's every edge created at any time. And then what we're doing is we're essentially extruding this, we're pulling this up so that certain edges, what we would like to do, if we could display this in a giant stack, right? Where, I mean, the problem of displaying space as a function of time and keeping the edges positions consistent is a problem of pulling this up. I really need to get to Bernat here. I can come back to you later, okay? Can you have a bit of a think about this and get back to me later? Will that work?
Okay.
Okay. All right. Let me talk to Bernat here. Okay. Thank you, Max. This is great.
Okay. See you.
Okay. See you. Okay. Sorry about that long digression here. Okay. So remind me, where is the best place to go find your trees and the tree code and so on?
The actual website, it's still like not launched, but maybe you can share you my screen.
Sure.
And then
go for it.
have several presentations, and the last one was in Canada. So
go on, just show me your screen.
Yeah. I'm gonna share that. So that's the.
Oh, whoops! Hold on 1 second.
Yeah.
No, I've just
Are you able to see?
Yeah, yeah, yeah. I
Yeah.
can see.
So that's the last presentation I did in December in Toronto in the CMS.
Okay, all right. So
Yeah. And there is, I mean, yeah, these
okay,
are.
all right. So let's take a look.
Yeah, for example, this is a particular family for the complex number is just one number, and the other one it's minus that number. That's it.
All right.
So
Can
yeah,
you?
I have this one.
Is there some code, some basic code somewhere that you could just send me that just makes a tree? I mean, I've got such
yeah,
code, but
yeah, like it's the ones that you are doing in the new kind of science. Yeah,
I know.
and nesting them. So yeah.
I know. So we can do that. Okay, I can do it again. Okay, fine. I've got that code, but I just wondered if you had nicer code for doing that.
Yeah, I have different versions. Like one is like using images for the more complex ones. When you have overlaps, then you get nice limit sets of that.
Okay, but let's try to understand. Let me just try to understand what the basic point is here. Real 08 dash continuum actually dash trees. Okay, so let me remind you what the point of these. So normally we have this idea of, you know, something like this, right? So this is a something where at every step we're taking the states, we're taking a list of states we got, right?
Right. Yeah,
and that we're applying. So we can think of this as at every step we take every state and apply a function to it.
Yeah.
Okay, so in particular, what that means is it's kind of a nest list. It's a multiple nest list. Okay, so it's like a multi-way. I mean, actually, we already have. This is like a multi-way nest list.
There is this paper for the Bridges conference I published last year, and I was using these kind of substitutions for getting to the boundary of a particular family. I was calling Fern like complex trees, and you should find the paper. But that's let's keep there. Yeah. So, but this is like an example I have in mind.
Okay, so hold on. So basically, the idea is there's a multi-way list. Okay, so then we have initially states, which is a list, and t, which is an integer. And what we're doing is, at every step, we're saying, take the elements of f. Okay, how do we do this? Is it an outer? What's the best way to do this? Is it a, for every step, right, we're going to say, oh gosh, help.
Nest.
What?
With a nest or like nest?
No. Do you understand what I'm trying to do?
Yeah,
I'm trying to just write the individual step thing, which takes each element of f and applies it to each of the states. Do you see what I'm saying? So I'm saying I map. Okay, so let me just see. It's a fold, is it? No. Yeah. Is it? What is it? Gosh, why am I getting confused here? So if I have f, g, h, and I have x, y, z, and I want to, oh yeah. Look, it's a construct. I claim it's an outer construct. Yes, it's that. It's the flatten of outer construct, I claim. So it's a nest list of a flatten of an outer construct of f, comma states. And just for good measure, we'll say 1 there. except it isn't actually states, it's hashed there. And then we say states here, and then we say t. Okay, so now we say, so if I say, so let me make one of your trees here. So give me an example of functions f that I can put in here. They're presumably complex numbers of some kind, right? Complex multiplications.
Yeah, like one of the simplest is like getting z and I mean the conjugate of it. Then you get the symmetrical ones or
Okay, just give me a function that I'm going to apply to the states. So my list of states is just going to be the list 1, for example.
yeah,
Okay?
okay.
So what should that function be?
So like for example -1 minus z, like like you're applying this really simple.
Yeah, okay, -1 minus hash, and what's the other one?
And the other one is just hash. Yeah. So you have these two roles for like the each.
Okay, so what is that doing? That's not that exciting. That's going to make.
Okay, you have like you have to take the 1 plus this expression like 1 minus but I'm not sure what.
Just give me a tree. I can generate one also. It's got to have a complex number in here. So it's got to have a complex number. And it's got to have a scale other than 1 here. So what would be an example of such a tree?
Yeah, take like 1 plus this expression minus 1 minus.
Sorry. Just give me the expressions. It's the function of z. There are two. We're going to have two functions that act on z. What are those functions?
But you have to get some constant before. Like you have like the complex number and then the hash. So there is both.
No, but I understand. So just give me a particular value of the complex number. I'm just trying to make an example here.
It's for example minus 1/2 and plus 1/2.
-1/2.
Like the imaginary 1/2 as well.
Okay, so I over 2 minus I over 2 plus this, and then plus I over 2 plus this. Is that right? That seems implausible to me that there isn't a scale factor in front of the hash. But maybe there isn't.
There is. I mean, like this is like so you add 1 plus, and then you have this -1 minus I over 2, like with the hash multiplying it.
I'm sorry, I don't understand. We've got two functions. We're taking a complex number, right? And at every step to make the tree, we are taking that complex number and we are turning it into two complex numbers, which are some function of the original complex number z. What is a good example of the functions f1 of z and f2 of z that correspond to the two branches of the tree?
Yeah, and just I type it one of them.
Okay, fine.
And then you can take the conjugate of that.
Okay, so fine. So that's fine. Okay, great. That was what I wanted. Okay, so then it's this, and the conjugate of that is otherwise known as, oh gosh.
N minus I.
Yeah, in that.
And instead of like using half, like then.
I understand you can do lots more things. I'm just trying to get one example before we go on. Okay, one example. Just to understand what's happening.
Exactly.
So then this, okay, so now here, one of the things of interest, okay, so given this, we can say complex list plot of flatten of this, right? And we should get a nice tree, a nice sequence of trees, sequence of tip sets or whatever. Okay, so let's keep going. Let's go to 8 of them or something. Oh dear. Let's see. How do I make this so that I can actually see the things?
Like it or
How do I do? It's just with complex list plot. How do I
connect the dots?
Arrow thick. What's that? Okay, there we go. Okay, so that's a nice C curve.
Yeah, well, maybe.
Sorry?
Yeah, like the curve.
I'm just asking, how can I
Yeah.
make this so I can actually see it?
I think we are just plotting the dots. We are not seeing the edges.
I know. I was just trying to solve a much simpler problem.
Yeah, sorry.
Just to make the dots so that they weren't invisible.
Yeah. I see.
Okay.
Yeah.
All right. Now I've got the dots. Okay. All right. So now I can also plot. So to make a picture like this, I also could be plotting the edges. Okay. But the important thing here is, let me point out.
I think an interesting example will be to take the to multiply by -1, like, and then you will get like a gauge curve. So we can layer down. We can have each level to have a height, so it's a 3D, and then you can see some nodes that are colliding together.
Okay. I would very much like to see that. Okay, so then I'm trying to understand here. So this picture. All right, so here, so I should get, if I was on the real line, if I was projecting everything onto the real line, I will get a picture like this.
Right.
Right?
Yeah.
Okay, so one of the things, okay, now here we're showing the events, and those events correspond to the different functions here, F1 and F2, right? I mean, because we're labeling these edges by whether it was an F1 event or an F2 event. Am I making sense?
Yes.
Okay, so now one of the questions is, okay, so one thing that we look at here is this so-called branchial space, which is the space that you get by looking at which pairs of states here are connected by having branched from the same state on the previous step. Does that make sense?
The ancestor, yeah.
What's that?
Yeah, the ancestor, yeah, ancestor.
Yes, right. But so let me show you, for example, here that if I go to 8 steps, for example, let's just do 6 steps actually, and let's say, okay, so that rather boring graph gives the relationship between these events here, between these states here. See what I'm saying?
Yeah.
Okay, so in your case, I'm just wondering what the analog of that is. So, and one of the things that will happen, so one of the interesting things about your case is that you know what the limit set is. You see here, we don't really have a very good notion of a limit set because we're dealing with things like strings and so on, which are hard to connect together. In your case, you have a notion of a limit set. So in other words, this thing here, if I were to go, if I were to just take the nest, the last of this, and I were to say like 12 steps or something, then I will get, what's that?
You're getting closer to the limit set, yeah.
Right. Now, that limit set will contain, as I understand it, many points where things reconverged. Is that a true statement? In other words, many of those, if I were to do path weighting, okay, so let me show you something. Okay, so you understand that, and what I could imagine is I could put a measure on this set by saying how many paths lead to each point in that set. Have you tried doing that?
I played a bit with these kind of like functions of like distant functions and also, but also I'm from the limit set. if it's from a nice algebraic number that you generated, the detractor, then you can get some structure. For example, just getting the nice boundary where you get this kind of a spiral thing. So you get to the front part, but then you remove all the branches that are going to
but so let me look at what I was going to do here. So what I could do here is, in this complex plot, I can ask the question before I flatten this. Okay, so let's just do this, and then let's say for 7 steps here, and now let's say I ask the question. I just do accounts of this because I've got exact numbers, right?
Yeah.
Okay, so in this case, nothing reconverged.
Yeah.
Is that a fair statement?
Oh, there is like one that's like 2 numbers, like you get some.
Well, wait,
a few.
Oh yeah, there's one there.
Yeah.
Okay, fine. So then if I were to look at the okay, fine. So if I were to say counts of the counts, so to speak, okay, so let's do accounts of values of that. Okay, so now if I go to more steps,
it's always, yeah, I don't think you're gonna get more than 2.
Okay. Okay, so now one of the things that I would expect is there exist choices of these numbers that, so in these systems, there's this notion of causal invariance. What does causal invariance mean? Causal invariance means that every branch will eventually reconverge. So the question is, does that happen in your systems? There must be cases, yes, it must happen when these things are inverses of each other.
Yeah, and there is a way to try to find particular rules that apply to a particular example. But the problem is how to isolate from other rules that are also applying to the same example. There is some nice, so you can try to find nice examples for each kind of rule.
No, but I'm asking for a different thing. I'm asking for, is there a case where every time there's a branch, there is also reconvergence?
Yeah, like for example, the inverse I was telling you, that like the inverse of this C curve is the Cauchy curve, and you're gonna get that's converging each time it's branching.
There should be a specific pair of numbers, or pair of functions here, that will give me that. What is that specific pair of functions?
It's just like instead of 1, like 1 plus I, you have minus 1 plus I.
Okay, so let's write it down. So hold on. What do I put here?
Like 1 plus I instead of it's just with a minus.
I'm sorry. We take out the 1 plus here. Is that right?
No, this is there always for, and then you have minus 1 plus. So
in here,
and
-1
then also in the other side, minus 1.
In here.
Yeah. So that's like negating, and that's one of the.
Okay, so in that case, so you're saying to me, in this case, what will happen is, so if I do the analogous thing here, what will I find? I will find here that, so let's see, that was -1.
It's happening.
Most of the time, everything is at least pairwise.
Yeah, it's pairwise, yeah.
Okay. Okay.
But then
can it be more than, I mean, so if we look at this picture, so I'd like to draw this picture for these things, right? So this is a 3D picture with, I mean, in principle, so let me ask another question. If I just did this on the line, not with complex numbers, are there interesting cases here?
Yeah, for example, the golden ratio, like the inverse of the golden ratio, is going to give you,
Okay, hold on. So then
it's going to be to the,
Are you about to send me a piece of code or something?
Yeah, I can try. Yeah.
If I mention this stuff, there is a place I can point people to in your publication space, so to speak. Is there or not yet?
Yeah, like there is the preprint and also this Bridges paper and also the master thesis.
Okay, good.
This thesis. But yeah, and so do you wanna this example, right?
Yeah, so I want this example, the 1D example.
It's so yeah, it's just like taking the inverse and then also minus.
Okay, so then here we've got this, and then you're saying it's 1 minus that as well. Is that correct?
Yeah, exactly.
And it starts with 1 here, so we say 1 minus this.
Yeah, exactly.
Start with 1, and we say 5 steps, and we just say okay. All right, so then if I say simplify that,
yeah, I think it's gonna work. Yeah, it's much nicer. Yeah.
Okay, is there a root reduction thing that will give this or what? So
yeah, I think it's like these are like just like powers of like inverse powers.
No, but is there a function like root reduce or something like that?
To get the polynomials?
Oh yeah, there we go. There we go. There we go. There we go. That's the one.
Yeah, yeah, that's the one.
Okay, so this will give us, is that in canonical form, I wonder? So then for each one of these, we'll say counts. I see.
There is some tools.
Okay, so there's many things which are, okay, so if we do the counts of the counts.
It's
interesting. Okay. So, all right, so let's take this. Let's do it like 8 steps. And then let's say, so I think this is going to make one of these, if I plot this, okay, 16, 20, 24, okay. Okay, so what you're now saying is if I were to take this and, okay, so here, take that, and then I say this, and I want to say map indexed.
You can add like an imaginary value to that.
Well, I was just going to do I was just going to do a map indexed here. So I'm just going to say map indexed of hash 1, comma minus first of hash 2, and then I want to do that over that, and then I just want to say, well, actually, I could just put point in there, and then I could just say graphics of that.
Yeah.
And I am pinked. What did I do wrong here? Multi-way nest list. Oh, I want to do that at level 2. Okay.
It is, yeah. That's one of the basic examples, but there are many when you start playing with different values instead of getting the goal. Yeah.
Okay, so let's see if we go, let's say 8 steps here. Okay, so that's a tree. That's just a very ordinary tree, and what we will see here is many convergences between in successive steps, right?
Right.
So we're saying, okay.
You can.
And, yeah. Let's draw the actual tree. Can we draw the actual tree?
I was gonna share the picture of that.
Okay, go ahead.
So it's like yeah. So I was showing you like this is one of the elements of that map, and that's the picture of that tree, but that's like going upside.
Okay, hold on.
So you get these nodes each like 3 levels, and this
Okay,
is like
hold
this
on,
little
hold on,
piece
hold
here.
on, hold on.
Yeah.
Can you make that bigger? Sorry, I'm just.
I think. Let me see.
It's just tiny there. That looks like a tweet or something.
Yeah.
It is a tweet. Okay, I can see it. It's all right.
Yeah.
I can see it.
Yeah.
Okay, so let me try to understand that. Okay. Yeah. So in the world of multi-way systems, yeah, that's a causal invariant system. And if I were to take the branchial graph of this, which is the graph that I get, yeah, I understand. Okay, that's nice. So I would like to get some code where I can actually plot those. But go ahead, yeah.
Yeah, and if you split those like in 2 pieces, then the 2 pieces, these 2 like straight lines are intersecting in this piece in there. So that's like where all the nodes are the same. Actually, right here when it happens, this collision, then you get duplicates for each node. It's going to be duplicated. So there is actually 2 nodes here, 2 nodes here.
I understand. So if you look at the path weights, by path weights I mean given you're adding up a bunch of path weights here.
Yeah.
And what does the distribution of path weights look like at the end? Is it some kind of Gaussian? In other words, if you look at the
like it should be. I think it's gonna be one of these non-differentiable plots.
Is it, or isn't it? Aren't the path weights at the end like Pascal's triangle? Isn't it a limit isn't to get to a given point at the end? Isn't the number of paths essentially the binomial coefficient?
Like for example, there is some uniqueness paths. Like this one is the uniqueness paths. There is never.
I see. Okay. Okay, so then I see. So then it probably is some kind of one of those Blancmange functions or something. Okay. Okay. So go ahead. Let me just understand this. So as a function of position, then this. Okay, the path counting. So what you've got here is you've got a notion of position in that final space. I get it. Okay, and you can ask for the measure with respect to that. Okay, I understand. All right. Yeah. So then, what is that?
Like this is like the antenna of this set. So that's like right when it's connected, and that's just for the binary case. That's all of them are unique, but they are connected. So you get this side line.
Wait. So that's the tree that corresponds in your way of writing.
1/2, yeah.
Okay.
Instead of using a golden ratio, you use a number 2, like 1/2.
Right, and then that's a dyadic.
Yeah.
That's okay. Okay, so as a function of that, so sometimes for some values, so what determines how much recombination there is? What property of the number determines how much recombination there is?
It's, so like this is a family of that's called multi-Nachi numbers, and these like the roots of these kind of polynomials.
Okay.
And you start getting like so it's like trying to to pull apart these two pieces that are connected. And as you are trying to pull them apart, you're going to find like other intersections, like these two nodes, you make them to collide. And then it's one of the dots in there. So the next multi-Nachi number is this big dot, and then the following one. And the limit is when you get to the 1/2.
Wait a minute, what is that thing you're showing down at the bottom of the page? What is that map?
Yeah, like this is like the roots of polynomials of coefficients 1, -1, and also 0. But this is like, for example, is when you take the complex number z, and then the other one is it's the minus z. So you're like here it's just the imaginary, pure imaginary. That's I over the square root of 2. But as you are like moving your complex number, you're getting different values. And right here is when you get these lines. But I was using this method.
Hold on. Yeah. The picture that is in the background, what is that picture?
Yeah, that's the locus of connectivity. So in gray, it's all the trees of this form that you take one value and then the other branch is the opposite, which are disconnected. And then as soon as you get to this region, you find that there are leaves that are connected and the topology is connected.
Okay, so hold on. So you're saying in the central region there, the tree has the feature that nothing ever reconverges.
Exactly.
Okay. But so that region there. So now, okay, so then the things. Okay, so that's the map of where it reconverges. Okay. But so now, if I were to pick an arbitrary point, is it dense? Is the set of reconvergent trees in that outside of that central region?
Yeah, there is a proof that's actually dense when you take this one disk of a radius 1 over the square root of 2. So from this part is completely dense, but when you get closer to the boundary in this area, actually, if you go, you can find holes in the interior. So
okay. So wait a minute.
Actually,
so can you click anywhere in this picture?
Not yet. That's one of it was like a kind of sample thing I did in December.
Okay. So in other words, the dot.
That's the goal. Yeah. So some of the relevant elements, because I was like plotting the different polynomials. So like the degrees that are lower, then you get a bigger dot. But as soon as you get higher degrees, you get closer to the actual thing. And I was also making maps of the ancestors of these elements. So you can like find which ones are corresponding. And it's actually branching. I can show you pictures of that maybe. So that's like these kind of maps
Okay, so hold on a second. So the first question is, I mean, the thing that I was interested in was that p-pole set, but what you're looking at here is the set in which there are recombinations of branches of the tree, in which basically polynomial equations for which there are solutions effectively, rebranchings correspond to solutions of these iterated polynomial equations. Is that correct?
That's correct, yeah. But that's for a particular family, this z minus z.
Okay. Wait a minute. Z is not. What's the independent variable? So wait a minute. This is the. Yeah, you're saying z goes to what? The original z goes to what function of original z?
Yeah, so z goes to minus z. So that's like taking the mirror. So if you're taking this dot, you're taking the minus golden over golden ratio.
No, so I understand that, but I'm asking in the iteration that generates the tree.
Yeah, so it's exactly the same we got. It's 1 plus the contractor with a hash. So instead of the contracting number, it's z. Yeah.
But this plot is in the complex plane. Let's call this plot a function of, you know, let's call the coordinate in this plot alpha, for example, okay, or lambda, whatever you want to call it. This plot is a function of alpha, let's say. What is the formula for the tree?
Yeah, so it's 1 plus alpha and plus the hash, the contracting, like the number you're going to be iterating. Yeah.
It's 1 plus alpha plus, well, let's call the number we're iterating z.
And then the other one is like 1 minus alpha, yeah, or yeah.
Okay, so then, okay, so then this thing is in the alpha plane, and it's simply looking at those sort of iterated linear iterates like that. Okay. I don't quite understand. I would have thought the hash had a multiplier. Doesn't it have a multiplier?
It's a alpha or the lambda, or in this case.
Okay, so wait a minute. So the actual formula is 1 minus alpha times hash and 1 plus alpha times hash.
Exactly.
Is that correct? Okay.
For this family, for this set, you're seeing.
Yeah. Okay. Fine. I see. I understand.
Yeah.
So then on the real line, which is what you're showing me there. So is this a genuine picture on the two sides? Is there a little thing that pokes out on the real line there?
Like.
What is that thing that is poking into that region in the center?
Oh, like this one is like to show the center, and you get this antenna. It ends in this element, but then it was like.
Why is that connected in the center there? I thought you told me.
It was like showing the z. I mean the real axis with the imaginary axis, and so I was showing both elements that are right in these two boundaries. So this is like this dot there, and then you get what's known as the H3, and it's also the same ratio of the A4 papers.
I'm confused here. Is this something in which there is recombination or not? In the H tree, there's no recombination, right? The H tree is disconnected.
Yeah. So the interesting part is what happens in the interior part, and that's like the boundary it's where you get just like connected things, and that's not going to be interesting. The nodes are not going to be colliding in this sense.
I'm sorry, where?
It's the way it's geometrically constructed, this family. So in order, yeah.
Okay, the thing I'm trying to understand.
Yeah.
We have this notion of causal invariance. Causal invariance is the property that any branching that happens will eventually reconverge. That is, that any 2 points that are distant, that are separated by branching, will eventually have as at some point in the future will converge to the same point. For which of these trees is that the case?
It really depends on the example they are picking.
Well, I mean, in this family of 1 plus minus alpha z.
Like this one is one of the ones I look at because it's related to the Rousey fractal, but so I can. So that's the kind of like structure you get in 3D, and that's when you get these kind of nodes that are connected, and that happens every 4 steps.
No, I understand that. You gave me a nice 3D printout of that, but what I'm trying to understand is it the case that every thing that branches subsequently reconverges? Do you understand my question?
But I mean,
you may not know the answer to that.
I think there is some examples I can tell you that, for example, this case is like branching in these two ways.
Yes.
And then it's like the Koch curve, but morphed in a way that you get also some other collisions.
I understand, but you're telling me that some things reconverge. I'm asking you the question: are there cases where everything reconverges? Right, where every pair of points that are separated by a branch, eventually one of their images is the same point. Do you get what I'm saying?
Yeah,
So in other
but
words, the tree has the
yeah,
feature that
like something that's very overlapping, but
yes,
but
yes. But I don't know whether it overlaps.
Still, yeah.
In the system that we have,
Yeah.
we don't need to have. It doesn't. It's just there exists a future iterate that reconverges. You see what I'm saying? So I mean,
Yeah, but here we have the problem that there is a set of uniqueness, and that's these kind of like branch paths that never gonna be like collided by another node.
Okay. So you're saying that there exists.
If you remove those, maybe.
No. I don't want to remove those. I want to understand those. So you're saying for any given alpha, there exist paths. So for any initial condition, there exist paths that will not converge with other paths. Is that correct?
Yeah, correct. Yeah, like for example, this in the boundary you get always these guys. Yeah.
Okay. Well, I mean, that might be an infinite case. It might reconverge at infinity, but it might not reconverge at any finite. But if you look away from the boundary, do they reconverge after finite numbers of steps?
Yeah, that's a good question. I don't know.
Okay, fair enough. Okay, so let me try to understand what the. Okay, so one question is this reconvergence question, and the other question is, by the way, do you have? Do you have nice code that computes? Well, you've clearly got code that computes that 3D image. Do you have code that computes? Well, I guess I need to work out for a given tree. I could just show the iterates in, for example, different colors or something. You must have done that.
Yeah, like yeah, got this. I was like getting these limits. Yeah, I have some examples when I'm using the color coding, and the color coding helps to get also the pathways. And in this particular example, I was only taking the branch paths that goes to the boundary. And the way to do that, you can also play with this. Instead of using 2, 1, and 2, I could be using A and B, but it's actually the geometry in the external boundary where you manage to get.
No, but I'm sorry. This 1, 2, etc. That's saying which of the 2 functions that you're in my multi-way nest list. There are 2 functions there, right? And so
yeah, 2 functions, and then I'm using the like color coding them. Like the 2 is in red, and then 1 is in black.
Right.
So like this particular piece is coming from these branch paths. It's like it's 2, 1, and 2, and that's like this piece in red. So
okay, I understand.
That's where I get this rule, and then the other rules are like these 2 other pieces. And from that you can get a lot of examples that are algebraically, and then you can find the boundary of them.
Okay, so hold on. Let me just understand what that means in my case. So that is saying for a given piece, yes. So that's the sequence of events that lead to a particular output state. Now, what you've done, as I remember, you have these recurring. You can use that as essentially a number system, and you can reference points in the plane in terms of their sequence of these digits, correct?
Yeah, that's correct. And yeah, so but like I did like several things, and one of them was exactly. I'm sorry. Like the different families. Like I was, for example, this one was for the von Gauche. So I was using this rule that these 2 branch paths have to be connected in this particular way. Then when you get this rule imposed in there, you simplify, and then you get that one parametric function, and that's the family of Gauche. And then I was making maps of these expressions. For example, that's like the plot for the Koch curve. So the ones that are symmetrical lives in this part that you may recognize from the set you were studying for the symmetrical case. But then now you can like break the mirror symmetry and explore different things. And as soon as you get to this kind of boundary, then you get intersections. Like this landmark is when this kind of structure happens, and there is this collision in there for the two pieces.
So hold on. So the thing that my set was looking at is thought about in terms of this multi-way system. It is asking the question. It's a little bit of a different thing. So for what dynamics, I'm just translating it into the for what in the space of rules. Yeah, okay. When do you visit? Yeah, okay. So it's a slightly different thing. But so I'm still trying to understand. So this thing that we call branch yield space, this question of at a given level in the treeing, what is the graph? I'm sorry. I'm still just trying to understand here. So okay. So one thing that we might ask in our multi-way systems and our discrete multi-way systems is the growth rate, given that you start at a point at the top, the growth rate of the number of distinct nodes that you end up with. So the analog here is you're asking as you go down, most of the time, you're getting exponentially many nodes, right? At the teeth level in your tree, right? Yeah. Most of the time, you have 2 to the t distinct points, correct?
Like in this example, or like?
No, I'm saying in general, if there isn't reconvergence, there are 2 to the t. If there's no reconvergence, then you will have 2 to the t distinct points at the teeth level, correct?
Yeah.
Yes, because every branch branches twice. So now, but many of them will reconverge. So one question would be, for what values of alpha you could map out as a function of alpha, you could map what the growth rate of the number of okay, I don't know what this is here, but you could map. Yes. Yeah. Do you understand what I'm saying? You can map the growth rate of the number of distinct points that you reach after t steps. So for some values of alpha, that will be 2 to the t. For some values of alpha, it'll be much less than 2 to the t.
Yeah, like yeah, for example, I mean, you can find like for these families I was constructing, I was finding the regions where the topology is the same, and in this case, for example, you don't get like nodes that are intersecting each other, so there is no like.
Okay, so then they're 2 to the t. Right. So that means that level t there are 2 to the t nodes.
Yeah, exactly, exactly. Yeah.
Right. So what's an example where there are many fewer than 2 to the t, where there's lots of overlap? That thing you showed me with the half and minus a half, that thing has huge amounts of overlap, right?
Yeah, and
in fact, I would think in that particular case that at the teeth step, the number of distinct points is of order t squared, not of order 2 to the t.
Yeah, and exactly, and there is there is many examples that you can get a lot of overlaps and.
Right, but I'm asking the question, if you're trying to compute the exponent, right? So it's 2 to the lambda times t, for example, is the number of distinct points after t steps. You see what I'm saying? Do you get what I'm saying? I'm saying how many distinct points at the level t, you're not yet taking the limit. At level t, how many distinct points are there? Right? So if there's, and the question is it the case? So you said that there are branches that never reconverge, that never converge with anything. There are singleton branches, but those may be at measure 0, so they may not contribute to that exponent.
Exactly. There's this, in this case, for example, there are measure 0, and one of them is the tip there and there, and but.
Okay, so what I'm asking is this quantity. This is essentially the entropy of, in this map. You're essentially computing the entropy of the map, because that's the number of distinct. You see what I'm saying? It's the number of distinct outcomes. And I'm just wondering whether you have computed that, or whether maybe Bill Thurston or somebody computed that. I mean, it should be the case. As a function of alpha, that varies.
Yeah.
And in particular, so for example, for me, an interesting question, is whether the set of causal invariant cases for which I believe that lambda is equal to 0 is a set of measure 0 or not. And I mean, that's a thing that could be probably determined. I could probably figure that out. Okay. What's the best?
Like one of the
Is this out there on the web? This document?
Yeah, this is like in the repository. I can send you the link.
Yes, please do.
Yeah, so that's like one of the neat examples where you get a bunch of like overlaps in different ways, but still there is some order.
But do you know what at the teeth level, how many distinct points are there? Do you know?
I know how to work it out for particular examples, but not in general. Yeah.
Okay. And what for the particular examples, is it always exponential in t, or is it not exponential in t?
I think it is, but maybe might be missing some examples.
Okay. I mean, I think there will be examples where it is not exponential in t, but
at least for the neat ones I was collecting in this particular way, but it might be the case that it's actually it might be the case that there are interesting ones, but I haven't been looking at them. Yeah.
Okay, fair enough. Okay, so now my question would be, okay, so all right, two other questions. So in your system, there are a discrete set of functions, F1, F2, F3.
Yeah, for like ternary trees.
Yeah, right. Yeah. But my question would be, one could imagine a kind of mathematical system where there are an infinite number of such functions. Go ahead.
Well, there is some dendrites or like things like that have been considered, not from the self-similar point of view, but there are some.
Right, but so one thing you could do is you could consider an F sub, whatever you call it, F sub Q, instead of F1, F2, F3, right? You would consider an F sub Q where you associate some measure that's a function of Q. So in other words, you say, I'm going to follow every branch for every separate value of Q, but I'm going to assign some measure to those branches that depends on Q. Right? So the measure you've considered so far is a set of delta functions in Q. Right? They're just discrete values of Q. But you could consider continuous Q if you wanted to. With a certain measure. So that's one generalization. And then the other generalization would be, instead of considering, and this is where I'm not clear how to do it, And instead of considering discrete steps, let's think how that works. So, oh, I see. Yeah, okay, so there's a generalization of this to continuous time as well. And the way that would work is this F sub Q, let me think about this for a second. Yeah, I think you can do that by having, right, I have to think about it a little bit, but I think there's a way of continuing it so that what you've got is a, you've got the analog to an ODE, just as iterative maps are a discrete analog of ODEs. Iterative maps have the feature that there is a single iterate at each step, right? And in an ODE, there's the idea that there's a single, the new value of y or new value of x as a function of t, there's a particular new value of x. Am I making sense? So what you need in order to make your kind of thing, you need something where at every value of t, you're spraying out many new values of x with a certain measure on those new values. So in other words, x of t plus delta t is some, so I mean, I think perhaps it can be thought of as a PDE. I'm not sure. I think it's a different kind of construct. I think it's a generalization of a PDE. Anyway, sorry, I'm just thinking out loud about what, I mean, I'm trying to understand. Your trees take the state space of my multi-way systems and make it continuous. Am I making sense? I may have been.
In some cases you can actually, get some continuous cases. Yeah.
Well, no. I mean, the things that I've been considering, for me, these multi-way systems are. Actually, okay. Here's the analog. So for me, the multi-way system. Yes, okay. I've got a big analogy here. Okay, so for me, the multi-way system. Oh, yes. Okay. So if you let me share again, I can write down.
Yeah. So I'm gonna stop. Yeah.
Okay. So analogy. So ordinary multi-way system has discrete states. Well, has states with discrete labels, with discrete labeling, e.g. A, B, B, A, whatever it is, okay? So now, first step is use continuous numbers to represent states, i.e., so that means, i.e., there is a geometry, there's a natural geometry on the set of states, which there isn't in the case of A, B, whatever it is. Okay, so then, right. Okay, so then the next question is, okay, so then the analog of causal invariants is various questions about the growth rate of distinct numbers, which I suspect, which probably, and the dimension of the limit set. Because if there's causal invariance, the limit set better not be dense. If the limit set is dense, I think,
like it's going to be, yeah.
Then it can't have reconverged. There can't have been lots of reconvergence. Okay.
Well, there is, yeah, some. I'm trying to think about some pathological examples. Yeah, I have to think it about.
Okay. So then the next question is, so for me, okay, what is the analog of branchial space? I don't completely know. What is its relation to the geometry of states? So in other words, what we're saying is that branchial graph that I had up here someplace, this thing here, right, is a map of states that only, so is it the case that in your geometry, that when you're generating one of these trees, yeah, if it's a branching at level 10 or something, that branching is geometrically close. That is, you don't, or is that not correct? In making this tree, is that right?
It might diverge. So it's like the node it's colliding, but then the next step is splitting.
No, but I'm asking the question, if I'm at level 10, for example, and I look at a pair of I look at the successors of a given node, okay? Are those successors nearby, or are they not nearby?
Yeah, they're going to be nearby, yes, exactly. So that they are contained, actually. You can say that they're contained in a disk.
So in other words, i.e., the geometry of state space is probably the same as the geometry of branchial space. That's interesting. Okay, so now my final question, what is the analog of Rullial space? That's the space of all possible, okay, so that's the space of all your alpha values. And what is the object that you would construct that is essentially a super tree? Let me show you an analogy. Okay, show you a weird analogy.
Maybe it was like this kind of maps that was like connecting the like different interior specimens which are related because of the rules.
Possibly. Let me show you something.
Like, yeah.
So this is for Turing machines. Okay, what is this? These edges join states reached by any possible Turing machine. Okay, so there are 4,096 possible Turing machines. Starting from that state, each arrow corresponds to a different Turing machine. Does that make sense?
Yeah.
So in other words, it's asking for all possible, you know, the question for your trees would be, for all possible alphas, where do you go and with what measure? See what I'm saying? So in other words, we start from 1, okay? So let's say start from, you know, z equals 1, then apply 1 ag plus minus alpha z for all values of alpha. So I think that's one of the pictures you've drawn, I suspect. So you're asking, what is that picture?
Exactly, that's like, this is like the set of these roots of polynomials, because when you get a collision, then it means it's part of the connectedness locus. So
Okay, so wait. So that your picture there is in the alpha plane, and you're asking for what?
As you increase the absolute value of alpha, then at some point you get a
Things
value
blow up.
where, yeah, exactly, the limit set is connected. So if it's the modulus of alpha is small, for example, the absolute value is more than 1/2, then it's for sure that's going to be a Cantor-like set.
Yes.
So it's going to be, all of them are going to be the same kind of topological trees.
But above some value of alpha, above some modulus of alpha.
Yeah. It's when things got interesting.
Wait a minute, you're saying for some value of alpha, all the trees are topologically the same.
Exactly. Like in these cases, yeah, it's the same thing that happened for the mirror symmetrical cases. Instead of taking alpha minus alpha, you can take alpha and the conjugate of alpha. And that's the mirror symmetrical trees. And it happens to be that it's contained, if alpha is contained in the disk of radius 1/2, then all of them are Cantor-like.
Okay. If modulus of alpha, so you're saying if modulus of alpha is less than 1/2, all trees are Cantor-like.
For these two particular families, because we can construct a family that all of them, all the space is connected, and even for each like alpha value, you get a different kind of connectivity. It's not going to be like the same. I can provide you some examples.
Yeah. Okay. But so.
Yeah.
So there exist values of alpha for which all trees have the same topological structure. There exist big regions of alpha for which all trees have the same topological structure. Is that correct?
That's correct. Yeah, that's some families that were studied before, but I'm imposing these new ones that are, all of them are connected, but still you can find some regions where they are topologically the same, and you can find the boundary when this changes, when this is lost.
I'm thinking about this. Very interesting. Very interesting. Humph. Okay, so in a sense, I mean, viewed in terms of my weird world, yes, what those boundaries will correspond to event horizons in this Rullial space in some very bizarre, I mean, very bizarre. Now, okay, but you're asking for a particular alpha, and I'm asking the question, gosh, it's a more bizarre question, because I'm asking, I'm asking for a much, the set where you look at all possible values of alpha. So at every, instead of just putting down, yeah, I need to understand this better. That this is
alpha could be like a functional, like a relation, right? Or like instead of using alpha and minus alpha, instead of minus alpha, we can replace it for example, like 1/alpha or other things.
No, but this is more extreme than that. But okay, I understand. Okay, very helpful. Can you send me, I mean, wherever the best sort of version of code to run to make trees and the best sort of version of papers of yours to look at? Do you have a?
Yeah, like I don't have like a clean like versions of that, but again, I can.
Well, if you send me two things. One, what is out there in the world that I can mention, and two, what is the? I think I understand more or less what you've been looking at. It's interesting. See, this follows the principle that any sufficiently cleanly defined model will be useful for something.
Yeah.
in the sense that, your trees, I think they're an interesting model, and they're typically, any model that's clean enough can be applied in lots of places, and this is another place.
And you have like a few like versions of that. For example, if I want to produce like clean images of the limit set, then I usually, instead of looking at as dots in the complex plane, I try to compose images, and then it's a bit faster. But so it depends on the things you want to look at. But yeah,
well, I don't know. I mean, yeah, right.
Model.
Okay. Yeah, okay. I mean, if there's a place where you've got relevant code, that would be helpful. But right, I think this is really helpful, and yeah, that's
thanks.
what I need.
Yeah.
Okay.
Yeah, it's also
okay, this is
interesting.
Cool. Yeah, right.
I should understand better all this Rulio space.
Well, I may try to. You may hear from me again in the next few days, because I may try to. I've been trying to understand. I'm trying to understand the continuum limit of multi-way systems, and this is a piece of that understanding.
Nice.
And yeah. Well.
So yeah, I will send you a few links, and yeah.
Okay.
And I hope I'm gonna get like something more clean next time. Yeah.
Sounds good. All right. Yeah. Thanks a lot.
Thanks.
Okay, and by the way, I'm really enjoying the stuff that you're producing for the MoMath project. There's a lot of.
I'm also enjoying and finding these artifacts very interesting.
Yeah, the thing we have to do, though, is to, I really would like us to find more artifacts. I think we've been really lame at finding these artifacts. And I think the challenge is, like, for example, one of the things I had wanted to do was find just counting, with numbers in different number systems, and we've had a very hard time doing that. Like, get me an example. I mean, for the Babylonians it was easy; they left tons of tablets.
Exactly.
But for even Romans, getting a place where somebody had written out the numbers from 1 to 100 or something, just written out in Roman numerals, we've never managed to find that, which I consider to be kind of crazy.
Yeah. Sure. Yeah. It must be some way to look at these kind of artifacts. And for example, this kind of like fake image of the dice has been opening me some like a lot of like Iranian museums that are not well known, but they have some images in there. But usually there is no translation to English. So.
Well, that's interesting. I mean, see, this is the thing. We can stop sharing here.